Thank you. Thank you so much for having me. I'm really excited to be here. I am director of the foundation. We're based in Austin. We put a little math square in the Chronicle, if you've ever seen it. And we've been mathing it up all over town for 7 years. So yes, thank you. We're going to do a little warm-up, because that's what math teachers do, right? And what we're going to do is we're going to look at 2 pieces of pizza. That is Miss Marty Knott holding 2 pieces of pizza, and you are going to think about the pizza from which they came. Which pizza is bigger? It's a really hard question. I'll give you a moment. Concentrate. Okay. In case you need a different kind of visual, which piece comes from a larger pizza? All right, everybody good? Here we go. So we are in training to play a game at the end of this presentation, but you are also already playing a game. If you turned in your month and day birthday, then you are playing the birthday game. And guess what, Nerd Night? You are having twins. You are. You are not just having one set of twins or 2 sets of twins. How many sets of twins do you think there are here tonight? 5, 2, 4, 2. There are, or were, 6 sets of twins that came through these doors. Yes, month and day. And I have prizes for the twins, and I want you twins to know who each other are. I'm going to tell you the dates, and then afterwards, maybe we can see which twins are here and get the prizes out. January 6th. February, yay, January 6th. February 7th. February 12th. February 17th. Oh, we got some happy February 12th. February 17th. Boo. April 30th. There's April 30th and October 10th. So we have twins from all those dates. There were about 67 people that participated. And my question is, are you surprised? I mean, there's 365 days in the year, and yet we have this many sets of twins. And the answer is, we shouldn't be. If we do all the calculations, the probability, today is my birthday, actually, right now. Thank you. And that's one reason I want to play this game, but I did not find my twin. That would be very unlikely. But the likelihood that somebody is going to find a twin is pretty good. In fact, if 23 people had come here tonight only, there would be a 50-50 coin flip chance that 2 of them would have the same month and day birthday. Which one, we don't know, but some. And up here, over 60, the curve at the top shows us over a 99% chance of one set of twins. So we are not surprised. This evening we are already in process playing the birthday game. Please collect your prizes. We're going to go through 4 mathematical topics, and then we will be ready to play the live game. I'm going to need 2 volunteers, so if you're really interested in volunteering, just start preparing yourself. There is a blindfold involved, so for each of you, you get to take it home. So there's that. Yeah. It's kind of spa version versus kidnapper version, but here we go. Topic 1. How sure are you that the Earth is a sphere? Does anybody have any first-hand evidence? Not some tricked up NASA picture that we don't know if it's real or not? Anybody? First-hand idea? Yes? Okay, yeah, you've seen that curved image they project on the windows. What else? Anybody else? We're thinking something? Yeah, the airplane? Yes. You can see the horizon and it looks... Oh, the picture in the... yes. So the pathway that we go. Great arc to get places. Yeah, so in 1657, a map maker and mathematician, Edward Wright, published his thought. And it was this, that how many of you have seen a lunar eclipse? Lots of people. How many of you have had the opportunity to see a lunar eclipse and then you slept through it or whatever? You could have firsthand seen a lunar eclipse. And Edward Wright says, we always see a curved shape. Okay, we do this with shadow puppet theater at MathHappens, so that's what we're looking at here, the shadow puppet theater interpretation of the lunar eclipse. But not only what do we see, but what don't we see? That's another question. We don't see the square, the triangle, the bunny rabbit, none of these. So we have evidence from what we see, and we also have evidence from what we don't see. That was topic 1. Topic 2. We're jumping around in time a little bit. That was 1657. Now it's 200 BC. Can a librarian, also a map maker, figure out the size of the planet with the information he has available to him? So we're going to take a look at what that information is. He's living in Alexandria at the top of the map, and he's got friends in Syene, which is now called Aswan, down there. He has some tools at his disposal, like a plumb line. Miss Marty has a plumb line. No matter how we adjust this thing, it always points straight down. If you have a plumb line, a weight, and a string, you have a device that points to the center of the earth. And if you have a cup of liquid in your hand, I hope you do, then you have a device that shows you the horizontal, right? Your plumb line is going to be perfectly vertical. You have a level right here in your hand. What else does he know? They had people trained to walk a steady pace that could help them try to figure out distances. And he knew, well, if you're in a car, you can go in 12 hours and 56 minutes. But his walkers estimated it was about 500 miles from Aswan or Syene to Alexandria. And he had a notion the earth was basically round. And he had one more thing. He had some information. Librarians were collectors of information. And what he knew is that in Aswan, down here, it's just on the edge of the Tropic of Cancer, and one day a year, the sun would shine down on the buildings. They'd have no shadow, and it would shine down into the wells, which means that the sunlight and the plumb line were completely together, parallel, aligned. All right. So what? So the plumb line points to the center of the earth. We could put a stick in the ground, right? And have it pointing to the center of the earth using our plumb line. But we still don't know the size of the sphere or disk that we're on. In fact, that same 500-mile piece of crust could work for either of these two pictures, right? He knows about, all he knows is what's on the crust. His spot on one end, the other city on the other end, and he's got the plumb line. We need more. What else? I don't know. Yay. So sunlight comes out of the sun in all directions, but when it hits the earth, it's as though we only have one ray of light, like a spotlight, and that's how we get a shadow, because everywhere on earth gets the same angle of sunlight. So if you're in Cayenne, sunlight's coming straight into your well. But if you're up there in Alexandria, you're looking at a shadow. And if you use your handy plumb line shadow gadget, the plumb line points to the center of the earth, and you line up your stick with the sun, you're going to get a degree reading. And that's what he did. He figured out that degree was 7.2, that you would need 50 pieces to fill up the pizza. And he multiplied 50 by 500, and he got 25,000. In the units he was used to using, that was 5,000 stadia times 50, 250,000 stadia. So the Earth is about 25,000 miles around. Some really nifty mathematical thinking, yes, sir. Well, this is a good question, and I don't know. I don't know that he knew how far away the sun is, but he knows the sun casts shadows, right? Does he know if the shadows are different in different places? I'm not sure. That's conjecture. We're not getting shadows from these light bulbs, right? It's a point source that goes in all directions. So that's a good question. All right. We're going to move on. How do we get from cholera to soccer in one nifty math experience? Let's find out. In 1858, there was a big cholera outbreak in London. Dr. John Snow, his real name, thought maybe it's the water, but he didn't know. They didn't know that. Thought maybe it's the water in the water wells. So he did something that was foundational to epidemiology, and in fact, this is the foundation of modern epidemiology. He mapped where are all the sick people and or dead people. They are the little squares that you see. And then he wanted to ask a question about the water wells. But the water wells were not at regular intervals. You couldn't say, oh, let's just put a circle around a water well and know who's using that well. He went to the detailed work of walking from every point in this region and figuring out which well was closer by foot. So if there was a bridge or something, he would consider that. Which way are people really going to go? And the Broad Street well is not in the middle, it's over here. So maybe there's some other well that's pretty close over here. I don't know, but he drew this region and convinced the city that the cholera was coming from the water well, and he did something really clever to stop this outbreak. Do you guys want to know what it is, or save it for later? You want to know? He did not have a big marketing campaign to tell people to boil their water. He took the handle off the well. Problem solved. When we talk about this study, we talk about it as being Voronoi diagrams. But Georgy Voronoi didn't mathematically describe these until 1900. He was actually a Ukrainian who was in the he was an imperial Russian mathematician of Ukrainian descent. So what are Voronoi diagrams really looking like? In the abstract form, they look like this. The dots, I hope you can see the dots. Those would be wells, and then the colored region around the dot would be everywhere that can get to that dot easier than it could get to some other dot. But we can turn this thinking around and think maybe those dots are something else. Maybe those dots are soccer players. And if all the players run about the same pace, the colored region around them is actually the part of the field that they control. In 2007, the advent of sports analytics in soccer, they used Voronoi regions to see who was controlling the field. If you have two teams, they'd have two colors, and you put the colors around the dots of the players, and you could see something that could tell you how the game's going from that perspective. You could also look at polling places. Where are people going to vote? And if you want to put one more coffee shop in the city, or maybe it's a pizza franchise or a McDonald's, and you want to know where are my customers going to be because they'll go to the closest place, this is the technique you would use. How is it really mathematically, though? We're just going to take a brief moment. This is in the Wikipedia on Voronoi. I'll just let this run. You can see the regions of control merge into each other. If you've had a couple drinks, you might want to watch that. Everybody good? You want to go one more time? They are not always squares. They have flat edges. They are not. They do not have to be 4. They can be more than that depending on how the dots are. Wikipedia, you can get to this anytime and watch this as much as you want. Okay, one more thing before we're trained up for the live thing. Question is, what is in this lake? We could try like draining the water out of the lake. Now we could see all the things in the lake. We want to know about the fish. Maybe we put some dynamite in there. And mathematicians are cold. I mean, they don't care, you know. But okay, maybe we don't want to kill all the fish in the lake. What else can we do? How can we get an idea of how many are in there? If you were to capture live and gently tag 100 fish and release them to swim around in the lake, and this math, like these others that are sort of tailored to the conditions, this is as well. The fish really have to mix around with each other. And then you go back a week later and you catch 100 fish. If 50 of those fish have tags, then there were probably around 200 fish in the lake. You use the proportions, right? I tagged 100, I let them go, I caught 50, then for every tagged fish, there's an untagged fish, so it's probably like 200. What if there's only 1 or 2 tagged fish in the second group? Then there's 5,000 or 10,000 fish in the lake. So this technique will give you an idea of what's going on without killing the fish. But then there's a trade-off. with the dynamite, you'd know exactly or if you pumped out all the water, you know, you'd know exactly. But you could have a really good idea. And figuring things out without doing harm is another application of mathematics that we don't articulate that way always. Okay, so now we're going to learn one more thing, which is tonight's main activity. This was a mathematical technique invented in 1943 by an economist named Robert Dorfman. And I need 2 volunteers. You 2? Oh, 3. Oh, are you 2 a couple? As a couple, can you donate us 1? And then I'll take you also. All right. Thank you. Round of applause. Okay. I don't know if I need your help, Mickey. I might. Here's your blindfold. And for you. So I think that I would like to have you 2, unless the camera, oh, now the camera's that way, be on either side of this table in the front-ish. So like there and there again? There and there. Okay. Does that work for the camera? Okay. So your job is going to be, I have 3 carafes back here with liquid in them. And our volunteers are going to tell us, I have some like Mio stuff. I'm going to color some of the liquid, and they're going to tell us something about these carafes based on what they see in these cups. So you guys are each going to get a cup, and you're going to be responsible for analyzing your cup. Okay? Think you can do it? Okay. So I have 3 carafes. They're going to be numbered 1, 2, and 3. And you are going to have cup A, and you are going to have cup B. Lots of labeling going on here. Okay? Okay. Let's try the blindfolds on. Let us know if you're comfortable. Good? Okay, so keeping in mind carafe 1, 2, and 3. Carafe 1 is going to get poured into cup A. And carafe 2 is also going into cup A. Carafe 2 is going into cup B. Carafe 3 is going into cup B. Very complicated. Okay, blindfolded people, you can remove your blindfold. What's your name? I'm sorry? John. You have cup A. Which carafes are in there? Do you remember? 1 and 2. What do you think your cup indicates? Keeping in mind that you're wondering if it has any of this bright red stuff in it. Pretty clear to you. So what does that imply about carafe? In where? Neither in 1 or 2. How do you feel about your cup? It's clear. So, okay. So he says there's no red stuff in carafe 2. You would agree with that? What's in your cup? Carafe 2 and 3. Yes, you have some of both. He has 1 and 2. You have 2 and 3. Don't overthink. Yeah. Okay, excellent. Good job. Blindfolds back on. I know, you guys. You have high expectations. Okay, here we go again. Same thing. Carafe 1 going into cup A. Carafe 2 also going into cup A. 2 going into cup B. And carafe 3 going into cup B. Now, before you remove your blindfolds, you are not going to be paid at all for this. But if you were paid something like $100 every time you analyzed a cup, that would be significant. But you're not. Okay, blindfolds off. What's going on with cup A? Yes. So what do you think you know?
So that means that if I couldn't see their glass, what I know is that either one.
Yeah, you can't see hers. You can only talk about your cup. What does your cup tell you?
My cup tells me that either 1 or 2 or both have red in it.
Okay, very nice. What does your cup tell you?
Neither 2 nor 3 have red.
So what together do you know? Together you know that it's 1. Right. So, but you know what? I'm going to go ahead and reveal. You guys, now if I had used a cup on each of these and had it analyzed, I would have spent $300. But I didn't. I did this, and I got a sure answer for $200. So that was pretty cool. Do you want to go again? One more time? I have 2 more cups, so. I know. You guys are getting good with the blindfolds, I think. All right. Here we go. Carafe 1. Carafe 2 going into cup A. Carafe 2 going into cup B. And carafe 3 going into cup B. Okay. Can everybody see the cups? You guys are all good? Blindfolds off. Now what? Maybe. Let's hear what you have to say about cup A.
Okay, so cup A looks like it's
Oh, this is getting fancy now, right? He's looking at dilutions. So what do you think is going on with the carafes?
So if I remember from last time, that means that either it means it should be the same.
Oh,
It means it should be the same, I think. So that would mean that one has red and two doesn't.
okay. Maybe one has red and two doesn't.
Oh, hi. That's that's like so embarrassing. Oh, okay. So mine is about the same color as his, and assuming you poured half and half, then it would mean that half does have the red stuff in it, and half doesn't. So either 2 or 3 have it, but that does look like the same. Well, I'm not allowed to see his, am I?
Oh, no, it's okay.
Okay, so I would guess that it's 3 that has the red stuff in it, or you could have been really, really, really sneaky and just put a little bit in number 2 and a whole bunch in number 3.
Okay, let's say that there is only one of the 3 carafes has any red in it. Which one is it? Shh.
Oh, sorry, it would have to be 2.
It would have to be 2 because
It's the only one that's the same between
it's the same between the 2. What if we don't know? If it could only be 1, it's got to be 2. But if we don't know, could all 3 carafes have red stuff in them? Or 1 and 3. So in this case, maybe I spent $200 on this, and now he's telling me it could be 1 and 3, or it could be just 2. If I can't see these, which presumably I can't, although you can, then maybe I have to go back and spend another $300 finding out what went wrong here. So this situation cost me $500. When it was this situation, I saved $100. And when it was this situation, I saved $100. What you've described right now and what you figured out is exactly the mechanics of what they call pooled testing. And I have put my clicker down somewhere. Thank you. Oh, thank you. And this is what Robert Dorfman invented. It is a technique for combining samples and testing for diseases and trying to save money and get more answers for less laboratory time and reagents. And sometimes it's just money, but it's also time in the machine. So they used it in the 40s for syphilis to test people before going into the army. In the 1980s, they used it for the blood supply to test for AIDS. And then in the 2020s and continuing on today, it's used for COVID testing. There are many, many varieties of it. They've just done a complex version called overlap. They've done a simple case of a complex construct called overlapping pools. You can use graph theory, or you can do something called simple pooling. And just going to show you that. This is what Robert Dorfman invented. I hope. Can you make it go? His version was simple pooling, and you two are going to get kits that have pH strips and vinegar, water. You can pool test at home. If it's got vinegar, it's going to show orange. So we put 1 vial in the rack, and then we start getting 3 drops from each vial. And we're combining our samples. We're going to test our pools. The second from the right is a little bit more orange. It's hard to see. We've already cleared 20 samples. We've only used 5 tests. And we're going to use 5 more and find the 1 out of the 25. So saved a few bucks, maybe saved some time, and got some answers faster than we would have before. And that is my talk on cool math strategies to solve problems. Thank you. Thank you to our volunteers. We really appreciate it. It's a pooled test kit for each of you.
All right, we have some time for maybe like 2 or 3 Q&As, and we will go ahead and go with Mickey first.
In the pool testing, in the third test where both were red, it was inconclusive. Would you really have needed to retest all 3 carafes, or would you only have needed to retest carafe 2?
Very nice question. This is a really good question, because if we test carafe 2 and it's positive, then we still don't know what's in 1 or 3. But if it's negative, then we know what's in 1 or 3. So there's something called adaptive pool testing. That's where you get an answer, and that answer leads you to do another strategy. It might be another grouping, but yes, you could have done that to try to not go all the way out to 5 tests used.
Were you done? I didn't mean to cut you off. Okay. All right, excellent. So we had 1 good question, and then we've got another one, hopefully also good. We'll see. No pressure. All right, let's see what's up.
I really like the another pooling question. When you're doing over large samples, like with COVID or AIDS or whatever, do you have to worry more about like type 2 error, where you just get a false negative instead of a false positive? Like, how much does that come into the issue when you're doing large samples?
Okay, so false negatives in pooled samples.
So I'm not entirely qualified to answer all these questions in every detail, but one of the things that pooling does do is it combines samples. So one sample might be in several different pools. So it actually gets tested more often. And in some constructs, you get an error signal. Like, in a matrix pooling, you pool across and you pool down. And if there's a positive in the across, but none of the downs come up positive, then something's gone awry, for sure. So yes, there's some argument to be made that you actually are testing more often that same sample, but there's dilutions too. There was one study I was really interested to read that was talking about how they did it in Rwanda, and they were actually pooling up to 80 samples together. And they also had a construct that was not just a grid, but it worked like a parking lot. So they had had 27 together in a parking lot, which parking lots are positive, and then they would take level 1s and put them together, and spaces and rows, and you would actually get an index for where that sample is.
All right, y'all. I think that is a good stopping point for us tonight. So thank you so much for coming to Nerd Night Austin. Let's give our speaker a hand.